This is the last part of the theory of adhesion. We will see how we can predict spreading of the adhesive and discuss the various theories of adhesion. In the previous module, we have basically seen the concept of the surface energy. But what do we do with that concept? How can we predict if an adhesive will wet or not, will spread or not at the surface of a substrate? That's what we are going to see in this module and discuss also other theories of adhesion and also the weak points associated to these theories. So we know now what is the surface energy of the liquid, of the solid. It's much easier to understand in the case of a liquid. We have seen the demo with the needle on top of the water. What do we do with that? Well, there are many ways to explore this, more or less complex with many equations, but there is a principle that is very easy and that works, which is the principle of minimum energy. And what this principle says is that if you have a surface of high energy, that of the solid, and this surface is substituted by another one with low surface energy, that of the liquid, then the total energy of the system decreases, and that's a spontaneous process. In other words, if you have a situation where the surface energy of the liquid is lower than that of the solid, then the liquid will spread. But if the surface energy of the liquid is higher than that of the solid, the liquid will not spread. So like this we can predict if we will have a good adhesion or not. Now, which materials have a high surface energy by nature? It's easy. It's those that are very hard. So metals, ceramics, by nature they are hard and they also have a high surface energy. They are easy to bond. Plastics, for example, they are very soft and they have also a low surface energy. They are very difficult to bond, all right? You have here an image that shows how an epoxy or which shape will form an epoxy at the surface of various materials, aluminum, PVC, a plastic, polyethylene, another plastic, or Teflon. Teflon is the worst case scenario, and you know that the Teflon is used precisely when we don't want it to stick. You see, it's nearly a spherical droplet. So really, it varies from surface to surface. If you know the surface energy of the epoxy and that or those of the surfaces, you can predict if it will wet or not. We can play a bit now and do a demo with various substrates, and we will put a drop of water on each of them, and you will see the shape that it forms. We will go from very hard to very soft. So I have this pipette, and I will put water a bit on. I will start with glass. Glass is very hard, and I put my drop, and you can see that it wets. It spreads very nicely on the surface. It's expected because it's very hard. I do the same now with the metal, with aluminum. And, well, the spreading is nice, but not as nice as the previous case, as with glass. It's still very nicely, but not as good as the previous one. Now, I go to a plastic. And again, it's getting round. The contact angle is increasing from this situation to this situation. It's very hard, less hard, and quite soft. And the contact angle is increasing. And finally, I have a cabbage here. You all know that cabbage is what happens when the rain drops, and you see, you have beautiful spherical shapes. Can you see? It's really, really nice, beautiful, okay? So, depending on the surface energy, the water will spread or not. The same happens if you use an adhesive, of course, but it's much easier to use water. Okay, so after having seen this, how can the user intervene? What can we do to improve matters? Well, basically, it's increase the surface energy of the solid. Those that naturally have a high surface energy, like metals, like ceramics, well, what do you need to do? You just clean the surface because all the surfaces, they have dust, they have grease, they have oil, so you need to remove these substances, and then you are left with a high surface energy. In the case of plastics, well, you can clean how much you want, but the substrate, the material itself, has a low surface energy. In that case, you need to apply a surface treatment to increase the surface energy. So far, the theory of adhesion that we have been discussing is the theory of adsorption. But it does not mean that's the only theory. There are other theories of adhesion. You have the mechanical, the diffusion, and the electrostatic. These two are not very relevant, especially for structural bonding. This one is the major one, but the mechanical one is also quite important. And in fact, it was the first that was proposed and can explain many cases. But let's do a recap of the theory of adsorption. Basically, it says that when you approximate sufficiently the molecules of the adhesive to the substrate, boom, you will have van der Waals, and you can have ones that are stronger than others. The polar ones are stronger than the dispersive ones. You have a particular case of adsorption, which is the chemical adsorption, which is when you have a chemical bond. But in that case, you need to apply a special substance at the surface of the substrate to cause chemical bonding. And this will give you, of course, a higher adhesion and a higher joint strength. But let's look at the other theories of adhesion, the mechanical one. This scheme is very easy to understand. As you know, there is a roughness associated to the surfaces, which is represented here in the substrate. And if the adhesive can penetrate into this roughness, because in general it can, if it has a good wetting properties, then after hardening, there will be the creation of an interlocking at the surface, like this, an interlocking, and this, of course, also contributes to the adhesion. In addition to this interlocking, because you have roughness, then you have an increase of surface area, increase of van der Waals forces. In general, you have roughness because you applied emery paper or shot blasting. This removed weak boundary layers. I'm talking about weak oxides. In general, roughness means better wetting, and finally, more energy dissipation because you will have plasticity of the adhesive at the interface. The diffusion is a very particular case, and it happens when you have welding by solvent or heat in thermoplastics. I don't know if you have seen in your life how the PVC windows are made, but basically you have two pieces that are joined together because they are heated, or the joining place. They are heated, a pressure is applied, and then that's how it's done. It's a kind of welding. But this happens because you have interdiffusion of the molecules of the two polymers together, and this causes the welding. But this can only happen if you have identical polymers. Different, it's a bit more difficult. They need to be compatible and miscible. They need to be below the glass transition temperature so that they melt. You can't be crystalline, and this is not applicable to metals. Another theory is the electrostatic one, again even more particular than the previous one, and this is especially applicable to the pressure-sensitive adhesives. I have shown you one pressure-sensitive adhesive when I did the demonstration about the peel. What happens is that you can consider this as a kind of condenser. One part is positively charged and the other part is negatively charged, and this causes attraction between the pressure-sensitive adhesive and the substrate. But this is not that important, this theory of adhesion. But what's important is to refer the weak points associated to the theories of the adhesion. These theories of adhesion that we have seen, they don't take into account these weak points. First weak point is the weak boundary layer. Why? Because the properties of the surface are different from the internal properties. It's unavoidable. You can have air inclusion, you can have formation of oxides, and the migration of substances at the surface. For example, in the case of air inclusion, if you have not a good spreading, like the one represented here, then it's very easy to have air entrapment here. And this is not taken into account in the theories of the adhesion. Another thing that is not taken into account is stress concentrations. Well, I told you that when you load a single up joint, the stress will be uniform. This is along the width, and it's true, I maintain what I said. But along the overlap, it's a different story. When you load a single up joint, then you will have stress concentrations at the ends of the overlap in the adhesive. We will see this in more detail in the section of joint design. So what does that mean? It means that in fact the stress is all concentrated at the ends of the overlap. The middle is doing nothing, and it doesn't really matter if you work with a short or with a long overlap, the strength will be the same from a certain overlap, which is what is shown here in this graph, failure load versus overlap. And again, this is a point that is not taken into account in the theories of adhesion. So, in conclusion, it's beautiful, this technology, but we have a big enemy. The enemy, in addition to the pill load, is the surface. And I leave you with this saying of Pauli: God created solids, but surfaces are the work of devil.